Hello, how are you? Thank you for the interest in this research. This work is about the electrochemical evaluation of polylactic, polycaprolactone, hydroxyapatite composite material in simulated physiological environment for biomedical applications. It is important to remember that the development of polymer-ceramic hybrid materials is of current interest, which may have several applications in the medical area. In this work, a composite material combining two polymers and a ceramic was developed, resulting in a hybrid biomaterial and evaluated electrochemically for later use. Polymers and ceramic synthesis were realized by applying different compositions of polylactic, polycaprolactone, hydroxyapatite over a stainless steel plate using the deep coating technique. Electrochemical and physicochemical characterizations were performed. The methodology for synthesizing the polylactic acid was by ring opening polymerization. Figure 1 shows the general chemical reaction. In Figure B, we can observe the hydroxyapatite synthesis where a relationship of calcium phosphorus of 1.67 molar was conserved. The polycaprolactone was purchased to Sigma Laboratories. For the project, several compositions of the hybrid material were made as we can identify in Figure C. The solvent tetrahydrofuran was used to mix the materials. The coating of the stainless steel samples was carried out by immersion by the deep coating technique. There is a photograph of the equipment we used to do the immersions. Posteriorly, the electrochemical behaviors of the composites were evaluated in simulated body fluid, with the compositions shown in Figure E. Each sample was evaluated for 40 minutes with a potential range from -500 millivolts to 2000 millivolts, a half cycle and a scanning speed of 1 millivolt per minute. The X-ray diffractions and spectroscopies show that the materials obtained have high purity and corroborates the crystallinity of the phases. The morphologies of the different coatings are observable in Figure H. Here, we can identify that the porosity of the microstructure is related to the increase in the added hydroxyapatite phase. The electrochemical reactions in the substrate interface represent a significant activity, and the increase in current density is directly related to the rise in the microstructure porosity because of the increase in the hydroxyapatite added. In congruence with this, it is identified that the higher the density of porosities and cavities in the coating, the greater the possibility of permeation of the electrolyte towards the metallic substrate, as well as a greater interaction of the medium between the porous microstructure of the composite material. The microstructural characteristic allows greater permeation of the electrolyte towards the metallic surface of the substrate, where oxidation reactions take place, with an increase in the anodic current density, as observed in the shift to the right of the anodic part of the curves of polarization. Figure I. In these results, the increase in the hydroxyapatite phase promotes a direct increase in the anodic current. With these results, we can conclude that the study of the effects of the polymer-ceramic coating on the stainless steel 316L yielded satisfactory results on the corrosion resistance behavior of these coatings immersed in the simulated physiological environment. As always, there is much more work to investigate, so we are continuing with the research seeking the best results in pro of the biomedical applications. At last, I want to thank to my research group for the contributions and, of course, thank you all for the attention. Have an excellent day. Goodbye.